Hello, everyone. My name is Jianfeng, and I'm coming from the Ant company named Ant Financial.
I'm Konstantin, and I do work for Intel.
Yeah. Today, we are going to present a work on the TLDK, a lot of enhancements on that. We will give a use scenario, serverless. We want to, so firstly, what's serverless? Serverless is the next execution model after the container, the microservice, and we want to provide a new model for application developer and application deployment. And so application user don't need to care about how to scale in, scale out. They just need to care about their own logic. And for this execution model, we see 3 requirements. So first of all, elastic and ephemeral. And so we need to provide very fast boot up and clean up time for the scale in and scale out. So, and the second thing, we want it to be very secure. I think everyone still remember the SAC panic issue several months ago. Even the Linux network provides the network namespace for the network isolation. But if we share the kernel, we could still be attacked by one of the instance. One instance get attacked, the whole server will get down. So we want isolated the stack for each instance. And the third thing is the efficient. I think nobody loves the slow path. And let's give some example on this. We test some container runtime using a simple Docker image, runc, kata, and gvisor. So for the initial memory footprint, runc is very low for sure, and kata maybe takes about 70 megabytes, and gvisor takes about 20 megabytes. And for the boot time, it's about several hundred milliseconds. And for runc, I think the most time are spent on the control plane. And this is for the whole instance budget. So what's the budget for the stack? Let's use the Linux DPDK-native as an example. I use a benchmark here in GitHub. I uploaded that in the GitHub. You can reproduce that. For the initial memory footprint, Linux DPDK-native, you need to spend about 300 kilobytes for a new net namespace. And for the boot time, actually it behaves different on different kernel version. In our version on 4.9, it's about 10 milliseconds to create a namespace and clean up the namespace. And for latest Linux kernel, I think it's about 5 milliseconds. So the budget is very low. So what we can do here? Before we go further, let's do some recap on the TLDK.
OK, thank you. OK, yes, so TLDK stands for Transport Layer Development Kit. It's a project, separate project under FIDO umbrella. Basically, what is it? It's not, at least at that time, it was not a complete stack, but a set of libraries that provide lightweight, high performance, and easily adaptable implementation of layer 4 protocols, mainly UDP and TCP. So it's built on top of DPDK, and it also kind of, I would say, it's extension of DPDK. So it even uses DPDK build system. Yeah. So it uses DPDK, different libraries, API inside, and also all external I/O API is MBUF based for packet processing, right? So it tries to follow DPDK main concepts as close as possible to process packets in bulks for receive, also try to accommodate as many packets as it can before transmitting to do things as fast as possible. Non-blocking API, all these tricks that we usually do in DPDK. The API, at least initial version, it was not compatible with BSD socket API, so of course we tried to use the same semantics whenever possible. You can find open, close, send, receive, and so on, so on. So just a quick overview. So logically, the whole kind of thing was divided into two parts, front end and back end. And basically, on the machine, you can have as many instances of TLDK, what we name contexts, as you can, right? As you want. So each TLDK context is basically completely independent copy of TCP stack, right? I suppose it's common way of doing things. In user space tags. So backend provides configuration API to create contexts, add devices, remove devices, destroy contexts, and actual packet I/O. So when you receive a packet, you want to send them for processing, you invoke this API, and vice versa. When you grab a packet from backend to send them over the actual network. Front end, it's all about stream control and I/O. So here you would see the usual user socket-like functions: open, listen, accept, send, receive, all these things. One thing to note is that front end is multi-thread safe, so you can have several threads running using front-end calls for the same context without any problem, but backend part is not empty safe, so at least right now, so basically for each instance of the stack, it's just preferable to have one thread doing all backend processing. Of course, you can have many, but then you have to provide your own synchronization mechanism. So that's the kind of the quick overview of initial set of libraries. And now we're back to real use case.
Yeah. So in our use case, why do we choose TLDK among a lot of user space stacks? So when we choose the stack, we want a DPDK-native TCP stack. So by DPDK-native, first of all, it should be developed by DPDK developers. That's joking, but I think some DPDK tricks, like the batching, prefetching, lock-free, should be in the code. Once in the presentation by Red Hat engineer, they said that the Linux kernel TCP stack lack such things. So why don't we choose a stack already have such things? So the second is like DPDK-native packet buffer. I see a lot of TCP stacks, they use a different packet buffer. Like FreeBSD use a FreeBSD MBUF, but DPDK use a DPDK RT MBUF. Even that will take only several cycles or maybe some cycles to do the conversion. But I think if we choose a stack, why do we choose a native stack? Okay, and the third thing is like we want a code can be maintainable. That means less code better. TLDK has only 10K line of code, and simple and clean. We want to make that maintainable because if we encounter any issue, we can solve that in about 1 hour or 2 hours. So we want to very clean design, clean implementation. And the third thing, like we want to invest in a stack which is very flexible. That means I will borrow a script from yesterday's presentation. Everything is a library. So we want to make this library be easily used in every kind of scenario. Okay, so this is why I think there are many other reasons we choose the TLDK. And, but even the TLDK, we still have a lot of issues to solve. But these are maybe not specific to the TLDK and even for other stack. First of all, it takes memory pre-allocation to get started. That takes a lot of memory. And in a serverless instance, scenario, we have a lot of instances in a server. In the second thing is like TLDK still like some test framework. This is also true for other user space TCP stack. And we need this for a reliable project. The third thing is like we need some layer 3 protocol for use, like SMP, ARP, or NDP, something like that. The fourth thing, even TLDK is very performant, but they use some not scalable data structure. So it requires us to estimate how many established TCP connection we need. And I think we don't want to configure such parameters in our case. Okay, so this is what's our goal, and this is what we can achieve now. First of all, ease of use. We want to make it very easy to get started, just several steps. Second thing, lightweight. We want to instantiate a stack by using 8 megabytes and in 5 milliseconds. I think we can do better. It's just some number here. And the third thing is the test framework. I think this is a must for the reliable stack and a must for a health project. Okay, first thing, preliminary ease of use. We want to provide a to-go option for users. So then the first thing is the BSD socket API. And people don't want to change their application before you tell them it can be accelerated by the TLDK. So I think I once worked at Intel, and we go to the customer and say, can you use the TLDK? And the customer asks, if you have a socket API, we can use directly. We say no. OK, so the game over. Then here, I think this is a must for the people to first get interested in the stack. And besides the socket API, we still need some FD management thing to do that. And the second thing is like how do we initialize the DPDK? We need some device queues configured, set up, or something like that. We want to we would provide a very easy way to do that. And third thing is the assistive but indispensable protocols. In the first implementation of TLDK, there's no such thing, but we now provide a simple implementation like SMP, ARP, NDP. Okay, on the right side, we provide an example to say how we can easily use the TLDK now. First thing, we start a tap device, and we're running a iPerf server on the Linux kernel stack. And then we give a virtual device. It's like a virtual user to the other environment variable. And then we give an IP, and then we run the iPerf client just using the LD preload. So just several steps to go. Okay, but we still need advanced usage for the TLDK. We want to, in some cases, we want to extreme performance, and we should make it very customizable. So first of all, library can be easily integrated into any project. And we can use that in LD preload, in any unikernel, in any Cisco virtualization implementations. So The second thing is like we should keep different kinds of APIs, customized API like the TLDK, original TLDK dual in the layer 4P library, and a POSIX API for easy to get started. And for the third model, I think this is most people care about when they trying to integrate with a user space stack. We can provide an inline model, we can provide nuclear side model, we can even provide a hybrid model. As Konstantin introduced just now, the front end of the TLDK can have lock and can lock less. On the right side, we show two typical usage of the typical thread model. One is the symmetric multi-thread. Every thread will have its own stack instance, but the FD management can be the one, and we need to properly manage the queue, manage the packet goes to which instance of the stack. And the look side model, application threads are running outside, and one IO thread or several IO threads running outside to provide the TCP or UDP service. It's still in the same process. And also, we still provide API for implementation for blocking or non-blocking implementation. So for non-blocking, previously we already have the implementation like event-based or callback-based. But now we go a step further to provide the IO event notification, like ePool, like select, like pool. Okay, so next thing is the memory footprint. If we are DPDK developer and users, we know that when we start a DPDK application, it usually takes about more than 1 gigabytes memory. So how can we reduce the memory footprint? So the most heavy thing is the MBUF memory pool. In the 1802 or 1805, Ananyev has upstream a feature named DPDK dynamic memory. That only works at the memory segment level. But here we are using a memory pool. We should provide the dynamic allocation and the recycle feature in the memory pool. And currently we implement that in ring-based or stack-based memory pool. And that can reduce us from gigabytes into about 100 megabytes memory. And we actually add a flag in the library to do that. And the second thing is like the string application and the recycle. Previously in the TLDK, the string are pre-allocated. And we'd like to say it is allocated in demanding. So Konstantin will introduce a little bit on the memory tank in the next slides. And the third thing is like some static variables in the macro we defined in the DPDK compiling. For example, if we change the RT max L core from 256 to 16, it can save about 6 megabytes. So such things we do a lot, and we try to reduce the memory. And another thing is the string table. Previously, we use a cook hash to store the established string. And that hash table is allocated for at the initialization time to store maximum string maximum entries we want to store. But cookie hash we'd like to a better implementation. We'd like a extendable version. But there's no good version now, and then we change back to the linked list hash, which is maybe performance a little bad, but the scalability is very good. And then we from dozens of megabytes to the 8 megabytes. And for the 8 megabytes, actually, we can still make it a little smaller through some configurations. But that is very good enough for our case, so we don't do any further. So the memory tank.
Thank you. Yeah, so initially TLDK used common, I would say, for DPDK application paradigm. When at startup you allocate as much memory as you can, you initialize all your structures straight away at configuration, and then at the runtime, right, you just use these structures without any additional memory allocations. And yeah, that's understandable. That's probably the fastest way. But as Jianfeng explained, it's probably not the case anymore, right? We have to adopt. So one of these activities came to a new structure, which we name memtank. It's just to show how close we are to original mempool. So basically, the same as mempool, it's allocator for fixed size objects. It tries to do that as fast as possible, probably not as fast as mempool, but hopefully close enough, so it could be used in various different cases. It reuses a lot of ideas from other fixed size allocators like slab and so on. So so basically fixed size allocation and free, plus ability to grow and shrink, plus some extra API for additional flexibility and support different usage models. So first one is, as I said, there is ability to shrink and grow. And these are actual function calls, so user can decide when it's time to do this. There is also implicit way, but I'll talk about it later. Also, there is extra policies or extra behavior for allocation and free. This is controlled via flags argument for memtank alloc and memtank free functions. So apart from that, user has to provide sort of a hard limit. What is the maximum number of objects this tank can have? Plus 2 thresholds. One is grow threshold. It's mean free. And another one is shrink threshold. It's max free. Yeah, again, I'll talk about them in details a bit later. Again, to be able to request and release memory from external memory subsystem, user has provided 2 callbacks, alloc and free. Pretty straightforward, just size and user data. For free, it's pointer and user data, and init to initialize just allocated objects. So then we could have all objects in pre-init stage, and we don't need to spend time of reinitialization. So yeah, the structure is pretty simple. So on the top, we have some fixed size queue. With current implementation, we use just last in, first out queue, but it could be any FIFO queue or RT ring or something. And that one is supposed to provide fast allocation and free. Then on the bottom, we have 2 lists of mem chunks. So as many other allocators, memtank requests big enough buffer from the host memory to be able to store dozens or even hundreds of these objects it would manage. Then it keeps some space from this chunk for its own metadata for housekeeping, and the rest one just splits into the objects and initialize them. So here we have 2 lists. One is in the bottom is full, which contains all such chunks with only chunks whose objects are all free for now, so we name it full. And used are kind of partially free or could be completely empty. And we put empty at the tail of our list. That would help us to know where to stop in this walk through this list. So yeah, so how it works in details, probably should go faster. So obviously, grow, it first check what is the number of objects in this fixed size queue. If it greater than our growth threshold, which is mean free, we do nothing. We just return straight away. If it's less, then basically we have to do some allocation work. So first we go and try to traverse our, no, sorry. So we do some allocation work. So we invoke user-provided alloc function, allocates one of several mem chunks, splits them into objects, initialize objects, and then populate our full list. Then, using this full list, we repopulate our fixed size queue. Shrink, doing vice versa. So at first it checks if the fixed size queue is full. If not, then nothing to do. If yes, then we are OK to go and shrink our tank and release some memory to back to the host. So in this case, we go through the full list and from the tail and try to return one of yours, them basically invoke free function for them. That's it. And now alloc and free. So obviously, allocation starts with the fastest path, so it goes into fixed size queue. Try to fulfill request from here. If yes, great. If there is no enough free objects, it goes. Again, it depends. Now it depends on the flags, right? There, where can you choose your behavior? You can either return failure straight away if the flags are 0, or if the flags are set, there is a flags alloc chunk. Then it goes and traverses this mem chunk list to try to find enough free objects to fulfill the requests. Then, even if found, great. If not found, again, there is a choice based on the flags. You either can return failure straight away, or you can go and call memtan grow if the flag alloc grow is set. In this case, it would basically do what grow does. So it would allocate more memory, populate more chunks, refill the fixed queue, and so on, so on, so on. Well, obviously, free does things in different way, but similar idea. So at first, it tries to put freeing objects into this fixed queue. If there is not enough space, it goes and finds the mem chunk this object relates to and put it over here. Now, if all of the objects for mem chunks are free now, so mem chunk become full, you move it into full queue. And again, now it depends on the flags. We either can return, or we either try to do shrink. Yeah, so yeah, probably out of time. Just so yeah, so when it comes to stream allocation, kind of the main two observations that should help with this model is first, usually in many cases, user can envision what is the load he wants to sustain without significant performance degradation. Let's say user can say, OK, I want to support up to 20,000 simultaneous connections, but I think that the kind of the usual load would be around 10K concurrent connections. And this gives an idea of what our shrink limit, what max free should be. So it's supposed to be basically something like 10K plus some gap extra to avoid any ping pong. Another thing, usually most DPDK apps, they work in kind of in polling mode. We have a polling loop where we do Rx bulk, then do process our packets, then probably retrieve packets that need to be sent and do TX bulk. So usually we're doing this Rx and TX bulks in some predefined numbers, like let's say you're doing Rx bulk maximum X packets, and basically that tells you that in just one iteration, you wouldn't be able to, you never would allocate more than X connections, right? So that gives you the idea of what mean-free threshold should be. Obviously, you want to be in ideal state, you want to keep this memtank in a stage where is this in more than this X number of free entries, and also you want to keep some empty slots for fast free, right? So so ideally that means that you still need to do grow and shrink, but ideally you would like to do that from the slow path to keep the memtank in the ideal stage. Now, we do realize that it's not always possible. Yeah, it could be high load, and it could be that fast path would try to allocate on free objects too fast, to allocate probably too fast. Yeah, but then there is also, because of this flag, there is also a choice what to do, right? Should we, let's say, when we have a new sync packet coming, probably if we kind of in a fast path and a critical path, we don't want to stop processing of other packets, so it's probably better to drop this one, but guarantee is a good processing of already established connections. But when we're going from the client side, let's say we're doing open and then bind and then connect, right? It's probably okay to do some extra work like alloc chunk or alloc grow, and yeah, so that's basically the main idea. The state is now it's work in progress. So the patches, I think it's version 4 now, are submitted to TLDK repo, but they are still not in the main tree. They are under review and under performance and functional testing. And I think it still would need several iterations before we have them ready for integration into the mainline. Yeah, also, you would probably notice that one big thing that this structure is missing now is, and would like to have, is per L-core or per thread caches, right, to make things even faster and match the mempool. Yeah, and hopefully, if this proves to be useful, we plan to move it to DPDK. That's it.
Okay, I think we are out of time.
Sorry.
So that is the memory footprint, and this is how we can reduce the boot time. I think I will leave this page for you to go through offline, and finally we get to 5 microseconds maybe, not microsecond, millisecond. And we also introduced something in the test framework in the TLDK. We add a package rail as a protocol test, and we also do some initial fuzzle test. But I think the stack test need more sophisticated fuzzling in the stack test. And this is what the green part is what we have implemented in the TLDK, but still under review. And the red chunk is what we think we need, but it's still not implemented. And so for summary, we want to make TLDK or TCP stack not only DPDK native, but also cloud native. And this is still underway to become a reliable stack. But we're happy to see patches, test results, and ideas in here. And the code is in the TLDK repo. And we'd like to thanks for the contributors in this work. So that's all for our presentation. Thank you.
OK, so we have a break at 2:30. So I know we overran the allocated time, but I think we'll take that next 10 minutes to go over a few questions. So.
This is Sun. I have one quick observation, and your memory library there looks like a lot what basically years ago the Samba team and Andel Tridgel invented something called Talloc, which lets you do layered grouped allocations and probably something like that would be useful in the DPDK inside our allocation libraries. And I would like to see code reused because that kind of stuff is pretty complicated and easily to get wrong. But having a general grouped allocation library. What that library lets you do is say, I'm starting a transaction, here's all the allocations for that transaction, and call one free at the end, and it cleans up all the chunks together.
Yeah.
And so that's kind of what you're doing with your grouping stuff.
That reuses a lot of ideas from other stuff, kind of, yeah.
Any other questions? Okay, so one question from my side. So you had mentioned scalability issues with RT hash library, with the Kaku hash library.
Yeah.
Did you try to use the lock-free version?
Which version?
The lock-free version?
Lock-free version?
Yes.
For the hash table?
Yes.
I think it's not the performance scalability. It's how many entries you would like to insert in the hash table. Yeah.
I see. So do you mean to say it was not extendable?
Yeah, I think we want to insert maybe 32K entries as established TCP collections in the hash table, but maybe we have more. So we don't want to configure the number to the maximum number as when we do the initialization. We want to, yeah.
Okay.
Yeah, basically avoid allocation of huge chunk of memory at startup. That's what we're doing now.
That's why
kind of.
we want to,
We have to be ready for the worst case scenario, so we allocate a huge one anyway, right? Even if we don't use it. So, yeah.
Okay. Great. Okay, great. I think it was a great detailed presentation. Thank you so much.
Okay, thank you.
Okay, thank you.